Our next speaker is Eric Drexler. He has, even in our hyper-educated group here, he stands out as having 4 separate degrees from MIT in a whole range of different fields, and is perhaps best known as the father of nanotechnology, which he helped popularize in the late 80s in a really groundbreaking book, The Engines of Creation. He's done many other nanotech-related things, and he will share some thoughts with us right now. 20 minutes time.
Well, I'm here this morning, actually a couple minutes into afternoon, to talk about manufacturing, a subject that the United States these days regards as rather antiquated, but I will be talking something for those foreigners to do, I guess. I'll be talking, however, about an information-driven revolution in manufacturing, information-driven in developing the foundational technologies, information-driven in running those technologies, and producing a physical technology that itself is remarkably much more like software, one that essentially can be thought of in many respects as treating atoms like bits. The topic here is productive nanosystems, by which I mean small machines that build things with atomic precision under digital control, and how this will lead us toward a super-exponential threshold in physical technology, a path where we can see already clear mechanisms for acceleration, for succeeding generations moving more rapidly. And before I proceed, I would like to mention that the affiliation there is not Foresight with an F, but Nanorex with an N. That's a company that is developing open source, freely available software for computer-aided design of molecules and molecular machine systems. It would be GPL'd if you track such things. So, outline of topics. First, as I've said, this is a technology that will treat atoms like bits. By that I mean as discrete entities that can be handled rapidly, where you're forming new patterns under digital control and doing so with extreme reliability. The same physical principles that allow one to manipulate bits in microscopic, increasingly nanoscale circuitry and do so reliably apply here. The two principles are noise margins, which can push error rates down exponentially as the margins get larger, and error correction. Second major point will be that enabling research is advancing rapidly. The foundations are being laid, that the path of this, as I said before, will be, I think, a super-exponential path. Toward the end of this path, we'll see a far-reaching transformation in physical technology, but nonetheless, there will, of course, be physical limits. So, looking back to 1990, this is a point for extrapolation, I suppose, if one wants to look at exponentials. A gentleman nearby here at IBM Albany took some hours to make a pattern of 35 atoms with precise digital control. 16 years later, we find these structures. There are a series of designs at the top in the top 2 rows and microscopic images in the bottom 2 rows. Each of these structures has roughly 1 million atoms. You make 50 billion of them at a time. And the paper, which was in Nature just very recently, earlier this year, is unusual in having being written in the first person. There's a single author, Paul Rotermund. I met him, a nice guy. And he is able to design and make these things with the turnaround time of about 1 week. They're DNA structures. DNA can be used as a structural material. Here's another example from last year's publication. Again, a group that can crank out things like this quickly and routinely, of DNA being used as a 3D structure. On the nanoscale, there are a lot of building blocks today that people make and are increasingly learning how to put together into larger systems. In the upper left-hand corner is a protein. We've heard it remarked that protein folding is a very difficult thing to simulate, taking gazillions of cycles per second and so on. Protein design, not simulation of the behavior of the molecule, but designing one that physics will then turn into what you want, takes hours on a personal computer. Protein design, designing nanometer scale objects with all the atoms in the right place and a lot of control over the structure and function, is now becoming routine, as is, of course, as I mentioned, the DNA engineering. The two fit together. So there are a range of other building blocks, organic molecules, nanotubes, various kinds of cluster structures, all of which are atomically precise. They can be made with suitable design to undergo self-assembly and solution to make larger atomically precise structures. And that's a path to making integrated functional nanosystems. with bits of metal and ceramic and semiconductor and polymeric materials. Well, we have an example of a productive nanosystem in the world today, which sets some kind of a relatively early target, I believe, for moving down one of several possible development paths. This is a picture. This is actually an object mapped in atomic detail. This is blurred out slightly to be more comprehensible, of a productive nanosystem, a ribosome. It takes in digital information from the genetic system and uses it to direct the assembly of small molecular building blocks into proteins. And in fact, the blue, light blue parts there are proteins, and the sort of spiral-looking tan parts are nucleic acid. If we look at this in comparison to some molecules that I showed earlier being engineered, it looks, let's see if we, not the most sensitive buttons in the world. It looks like this. It's pretty clear that we're making things of the right kind, nucleic acids and proteins, to be able, and the right scale, to be able to engineer things on this scale. It's a reasonable objective. People aren't there yet, but I think it's where we're going to be going in the not-too-distant future. So, looking a step beyond that, proteins are thought of as icky, soft things, mostly because people think of meat instead of one of these. Meat is mostly water. This is inedible, deadly, comes from another part of the beast. It's a cow horn, if you'd like to see it. It's a nice piece of plastic. That's protein, not meat. Nonetheless, it's only as stiff as typical, that's a sensitive button, typical polymers. This is something a lot stiffer, more regular. It's easier to imagine building with this. This is a sheet of graphite. What's special about it is that it was made by solution chemistry without anybody being able to put the pieces where they wanted, and fairly recently. The fact that you can make things like that without controlling where the pieces go in a direct digital fashion, I think indicates that a little ways down this pathway, we're going to be in a position to design things with materials like this that are intricate and can make structures, these are some slightly different materials, but structures something like this. These are examples of the kind of molecular machinery that one should be able to build when one can build things just one step beyond what I showed a moment ago. They're atomically precise structures. They do familiar operations in the mechanical world on a macro scale. And if you want to make molecular machine systems that do things, the tasks are fundamentally the same. You have to move things. You have to transmit power. Standard mechanical engineering approaches seem to be a very good way to go. If you think you can do better, then you're more radical. Okay? People will come along and say, this is very silly, biological approach is better. Fine, they're more radical. They think there's a shorter pathway, better functionality, that's great. I'm trying here to give some sense of where things can go, and if someone has a better approach, and I believe there will, certainly at the detail level, be enormously better approaches, that will be all to the good with respect to progress on the path. All of these were simulated, by the way, using the software package I mentioned earlier. So you can see that structures like that are in the same general class as moving parts like this. The atomic detail here is rather fine-grained rather than being the coarse atoms that you saw a moment ago. But rotating mechanical parts can do things like, with chemically active sites on them, bind molecules, run them through a series of processes where you activate them to make highly reactive molecular fragments, and then put them on building blocks to make larger building blocks working up to the macro scale. If you look at where that goes in building larger architectures, small mechanisms of the sort on the left there, moving down to the invisible molecular scale, can put pieces together that are put together to make larger pieces, that are put together to make larger pieces, that finally work up to the macro scale. It turns out this is a balanced production process in that all of the productivities of the different layers match up in terms of the throughput of mass per unit time. And molecules go in one end and they come out the other, and they follow some path. If they go at a centimeter per second and on the average, and the length of the device is a meter, then it takes them 100 seconds to get from one end to the other, to go from molecules to a three-dimensional atomically precise structure that can be very intricate. So that is a little bit different from macroscopic manufacturing in terms of the time for throughput from simple molecules to product. orders of magnitude better. I would also note that if you look at productivity, something like this can apparently produce its own mass in material structured to be of similar quality in a time on the order of an hour. If you ask how long does it take a semiconductor fabrication facility to produce its own mass in semiconductor chips, well, I haven't done that calculation, but it's not very relevant because it's never going to happen. One thing you don't see here is swarms of nanobugs making things. So this is an industrial-style production line, but scaled down. And in fact, you can see here's an example of a molecular manufacturing system shown outer side of a box in this conceptual design. You can see it's a very threatening thing. It has feet, 4 little rubber feet. You can see a grill there for a fan on the right. You know, it's got a fan to cool it, right? Plugged into the wall, touch screen, and raw materials coming from little bottles. What we're looking at here is an appliance, but one that can make remarkable things from simple raw materials and do so quickly and inexpensively. So that is the kind of picture of molecular manufacturing today. And it's been the one that has been around since 1992. And when you hear about nanobugs, that's an idea that is 14 years out of date. Please sink it. Self-replicating nanobots are not part of anybody's picture. So, backward chaining, how do you get there? Well, if you had one of those that was, if you wanted to build something like this, you could build one if you had one half the size. And you could build one of those if you had one half the size, et cetera, et cetera, et cetera, to get a minimal size. What's that? Something like 1/10 to 1 micron in scale. That would involve having things like this in that kind of volume to make your small mechanism that can make the larger ones. If you're able to make things like this, of this quality, you're in a position to make things like what I showed a moment ago. And if you're able to make things like this, but with intricate patterns, then you're in a position to make things like the previous layer. This is something we have, I think, in our sights in the research community, a stretch by ordinary standards, but a reasonable project to aim at. And we're already making things that are larger and comparable in complexity in terms of number of atoms, actually in this case far larger. Why do you expect acceleration? Well, cycle times will shrink. Takes weeks to make these structures, but they're fairly simple. It's going to take longer to design new instances of things like ribosomes, but ones that extend capability. But once you have those, design will be relatively simple and direct, and when you have ones that are good enough to make not just polymers, but things like this, you're starting to move into a mechanical engineering world where things are very designable, much more predictable, like these, which then, putting components together, which can be done rapidly. One can do the design before having the tools, so that when you have the tools, you're ready to roll and do a fast cycle of test and redesign. Can get you here, and so far it's all been stealth. It's microscale, making relatively small changes in the world. Then scale up can be rapidly, and you have a dramatically super-exponential process where this micro-scale technology erupts into the macro world and changes manufacturing and things on a large scale. What can this buy? Well, Moore's law has gone up to, well, we need another few years in there, going up to the billion transistor range. Technology based like this can give you a billion CPUs, not transistors, and put them in an air-cooled laptop computer. Being able to make small things on this scale has applications in medicine. Saw this image earlier. It's something with function much like a white blood cell, designed by Robert Freitas. And there in front of it you can see a flu virus to scale, perhaps an H5N1 virus. And to deal with that, you would program the thing to say, oh, here's what it looks like. Grab those and chew them up and dispose of them. Much better than trying to develop a vaccine that arrives too late. Well, I said you could make things on a macroscopic scale. This kind of fabrication facility scales up, and you can make pieces that get put together. You can make materials that are 50 times the strength-to-weight ratio of what the space shuttle was made out of. It makes it much easier to make things that go up high and fast. Provides a technology base that can clearly open the space frontier in a decisive way. We've looked like we're stuck on this planet so far because we're still in the hot air balloon stage of space flight. Yeah, making an analogy to aviation. However, this leads to limits. Trends don't tell you what the limits are. They tell you what you're doing within limits. And projecting forward, you run into a wall eventually in many different directions. Second law of thermodynamics, quantum measurement limits, speed of light limit. And a key conceptual point in thinking about this kind of problem is that where technology, as it progresses, is always expanding limits, always expanding capabilities, science, as Mark Miller pointed out to me some 25 years ago, is different. Its discoveries can revise limits up or down. It's about finding what's out there, not about achieving more. And we can see here various limits that were discovered in the last 200 years that appear to be solid. So physics sets limits. Now, I say physics, I don't say our present understanding of physics. Whatever the limits are, they're there. We may or may not understand them well enough to understand their consequences in a particular case. Nonetheless, physical law, and I think it's worth guessing that we understand it quite well with respect to the engineering domain of light and matter, provides a stable framework for thinking about the long-term future. So the picture looks like this: super-exponential hitting a wall. That's in quality of technology. In areas of complexity, the picture can look much more complex with a slower growth. Somewhere in there, I think you get machine intelligence, but this story does not rely on it. Rather, downstream, it supports it by providing a better substrate for computation. So I've reviewed the points: atoms like bits, rapidly advancing research, shorter cycle times and super-exponential development, a deep, pervasive transformation of physical technology, but physical limits. A key point with respect to development right now, and you timers, this is the last slide, is that while the technology base is advancing rapidly, thus far it has mostly been an unfocused effort. People are making more and more nanoscale things, finding out how to put them together, but only beginning to get a focus on productive nanosystems as an objective. Now, in the United States, one sign of progress is that bogus criticism has fallen out of fashion. It used to be that we had criticism at the intellectual level of, not this precise criticism, but at the same intellectual level of, you can't do productive nanosystems because you can't turn lead into gold. Okay? This is about rearranging atoms, not making new ones. It's at that level of absurdity of criticism. As I say, fallen out of fashion. In the US, we now have a technology roadmap project underway, co-sponsored by Foresight Institute and the Battelle Memorial Institute. It's an international technology roadmap for productive nanosystems. Battelle manages 5 of the US national labs. It's a heavyweight organization. Outside the US, I think there is less confusion in many respects. One indication is that journalists ask better informed questions. Another one is that R&D agencies are seeking planning advice on how they can take their expanding nanotechnology research and move it around sideways a little bit to focus on these kinds of system goals and productive nanosystems. And quite striking is that I've seen some speeches recently from a person in national leadership that reference the concepts. The technical book, I wish that people would not always say engines of creation. They would wish they would say, as the President of India does, Nanosystems, Molecular Machinery Manufacturing and Computation, which is a thick, technical, mathematical work in applied physics. That full title, in quotes, has been on the lips of the President of India in many of his speeches recently.